الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فايربيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmena.
السلام عليكم. مرحبا بكم جميعا في أحد session من sessions MENA Digital Days. We will be talking today about a simple introduction to JAX and how it can help us and help many researchers, machine learning in particular, accelerate their work and build more and develop more advanced machine learning models. I will be with Taha Bouhsine. I'm a machine learning researcher from Agadir in Morocco. I'm also the lead organizer and founder of TensorFlow user group Agadir. Today talks we will be mainly focusing on the main goals of this talk is to help you understand the basics of JAX and how it can help you in your research. How to apply, you will learn how to apply to the AutoGrad in the general solutions you will use, and we will be looking through simple introduction to Flax into the Flax library for deep learning networks, and we will be building another neural network with using Flax and OPAX, and also with TensorFlow data pipelines. The plan of this talk is mainly split into two parts. The first part will be an introduction to JAX, and the other part will be deep learning with Flax. So to start off, we will be starting with an introduction to JAX, or more like NumPy++. So what is JAX? JAX is an open source framework that's been developed by Google Brain that is suited for research work, including and not limited to machine learning, as it is used to develop other solutions also. It offers different features, but the main big features it has is the AutoGrad differentiation, and the XLA compilation that is used during the compilation of different function of your code, which makes your code faster. And I mean by faster, it can run on GPUs and TPUs, and it's just like NumPy, and with the ability to run on GPUs. So a simple code that is generally you can see it generally in any machine learning introductory courses. These functions or using the JIT function of JAX make the loss function and predict function have the ability to run on GPUs and on TPUs, or even on clusters of GPUs and clusters of TPUs, without having to edit or change anything in the actual function. Just running the JIT function on it will give you the ability to run on GPUs and TPUs. And it is as simple as NumPy, but it have the ability to run faster. For this example, we run the matrix multiplication on an array, a 3000 by 3000 NumPy array, and when it took us about 600 milliseconds to just run this multiplication, this computation. But when we used the JAX NumPy to run this computation, it only took it about 7 milliseconds. So you can say that how fast it is, and it was used during the ML-Perf competition back in 2020, and it scored. It was faster on more than one problem compared to other solutions, compared to other frameworks in that competition. And as I said, it is not only used for machine learning, it is actually used for building frameworks and building reinforcement learning frameworks like RLX, or that was built by Google DeepMind, or Coax that is built by Microsoft Research. And also there is an optimization library called Optax that is also being developed by DeepMind, and that is used with different deep learning models to optimize the weights of those models. It is also used for differential atomistic physics with JAX-MD, to simulate the molecular dynamics of the physics systems. And it is also used in Brax to build physics simulators that has the ability to run on simulate environments at millions of physics steps per second on TPUs and on other on GPUs. And there is also the main one is the Flax library that is built by Google Brain, that has the ability to develop and to train neural networks on TPUs and GPUs with a simple code base. And I know that you might say that you just learned TensorFlow, or you are learning TensorFlow. Should you restart, or should you switch to this new library? Well, this library is mainly focused on making research simpler, and the beauty of TensorFlow is not just a library for machine learning, for training machine learning models, but it's also for deploying and building pipelines and deploying machine learning models to web and to Android and stuff like that. It's not only necessarily used only for machine learning. It's a big ecosystem that have many more features, and Flax comes just to take part of neural networks for the neural networks, and Optax just for optimizing those neural networks. And you can use those the models you trained on Flax or in JAX and transform them into a TensorFlow format .h5 that can be used in TensorFlow Hub or in TensorFlow. You can import it to TensorFlow. So the main features JAX offers is the ability to compile your functions into to computations that can be run on tensors or TPUs, tensor processing units or GPUs, using the XLA library. It helps you just by making it using the decorators at JET before the function, give you the ability to generate optimized XLA code of it. And for every data type and shape, you can generate functions for every data type or for every data type or shape. And the only constraint is for the first compilation or the first call of the function might take a bit of time because it's trying to compile it. But when you try to run it again, it will load a cached version of the function that will be reused and will lead to a cheaper time or less time to run the function. The XLA compiles computations for CPU and GPU, TPU. For example, it's tried to compile this function into a code or XLA code that can be run on GPUs and CPUs from a single code. It doesn't try to generate. You have to customize your code for each of those environments. Why do researchers like JAX? It is actually an easy-to-use library. It's similar to NumPy. If you are familiar with NumPy, it uses function transformations, same as NumPy, and you can use the same code to run it on CPUs, GPUs, and TPUs. It is fast. It has some good performance, and you can simply parallelize your code using the Vmap, for example, to run across multiple clusters of cars or of sensor TPUs, TPUs, and the best thing is that it uses final programming model that is similar to how it is written in mathematics. How you find the actual algorithm written in mathematics, and you want to transform it into code. So you can use a similar. It aligns with well with math. It has reproducible results because we can control the randomness of those codes. It is easier to debug, and those are the key to JAX superpowers. And you might seen the JET transform, and actually quite handy when you are trying, for this example, when we are trying to call the apply forward pass in the first iteration, it took us about 2 seconds. And for the second iteration, it took us only about 0.1 seconds. It's made possible by using the object, the decorator, before the definition of the apply forward pass function. What does this decorator does is just it transform the function into a version that can be compiled and executed on XLA, or it generates the XLA code of this function and stock it in the memory. And then when we are trying to call the function again, it just look for the cached function by its reference, by using the reference as its ID, and then we'll be executing it again, which leads to a cheaper, or to say a cheap execution time compared to the first one. But not everything can be cached. To cache the functions to use JET, you have to respect some rules. And the first rule is to use only pure functions for JETted functions or for Vmap. So what is a pure function, you might say? And a pure function is just a function that the output of it, or the returned value of it, only depends on its inputs. And when you give it the same inputs again and again, it will always results in the same outputs. A pure function should not and does not use globals and doesn't have any side effects on the global variables declared or something like that. And the compiled functions, as I said, are cached and identified by their function references. And when you call, for example, the square function defined here, the JET version of the square function, it will take lesser time than the first time you call it, and it will give you the desired output of it. And as you said, the square of 2 is 4, and it doesn't affect. There is no side effect of this function. And another version of it, you can call it on an array of in your arrays, a NumPy array, GNP array, and execute it across all the data points you have. Why you should be using pure functions? Because they are easy to debug and easy to parallelize. as there is no shared state between the different executions, so you can easily compute them across different cores or different devices or different threads if you want to. It's able to be cached because there is no state of the function, and you can compose functions with it, with pure functions. You can call using the functional composition, and whenever there is a function, for example, equals z equals x plus y, you can the expression of it can be replaced anywhere with z without any needing to recompile the x and y. And what causes impurity is the use, for example, the use of a global variable. In this example, is the counter equals 1, which is a global variable. When you try to call it on a global variable, it doesn't change the global variable at all. When you call it the first time, it returns the counter plus x, and the first time you call it, it returns 6, and the second time when you call it, even if you change the counter to 10, it will still return 6 because the cached version of the global variable is still 1, and it doesn't change. Even in this change of the counter introduce, or the use of global variables introduce the impurity in your functions. Also, the I/O it is an external dependencies. When you call it the first time, when you call the I/O dependent function the first time, it will output the input received is 6, or it will print the input you gave it. But when you call it for the second time, it will not print at all the inner print that resides in the third line, the print input received. It will not print it at all because it's an external dependency, and when cached, it will not retrieve that dependency. And also, another comparison between where JAX is better than NumPy is the pseudo-random number generator, or PRNG for short. In NumPy, the NP random seed is a global, so you can, as we said here, we should not be using any globals. And when you are using a global number as a seed for your randomness, it will introduce some reproducibility issues where if, let's say, if the function A and the function B have a dependency or generate random numbers inside of them, when you call the first function, it will update the randomness of your function. So it will change the random seed of your environments, which leads to a lack of reproducibility, and it does not consume a state to have just like a fixed reproducibility. And it is a bit harder to parallelize and quite slow because you cannot run it on GPUs and TPUs. While JAX, on the other hand, it uses more G algorithm. It has they have reproducibility as a priority for them. And when you are trying to call a random n, for example, you have to pass to it a key, and that is consumed to generate a new number. And like NumPy, where you cannot, where the rand ends, for example, cannot consume any key or something like that, and it does not change or does not update the randomness, and or does not the random function does not update the state of the randomness, but it's just like consume it, and it's quite easy to parallelize it, and again, it is quite fast. For just when you are trying to generate random numbers in JAX, for example, whenever you call the JAX random split, it will give you a key, the actual key, and a new key that will be, you can use it to feed the random.normal or random.rand_end or something like that, to keep control, to have control of your reproducibility. And again, this is just the single for NumPy. You cannot consume, as I said, there is no key passed through the function. And for JAX, you can pass it, you have to pass it, round ends have to pass it a key. And also you have the ability to use asynchronous code in NumPy, where your code doesn't block doesn't block the execution of your code, similar to that used in JavaScript, if anyone is familiar with that. And when you call it, you call the function RNGs, it will try to run across all the inputs and will not block each other, so you can parallelize it easier. This is just diagram that is explaining how the async dispatch, but you can check the link here, the async dispatch in JAX docs to understand better. Another feature of JAX, or another transformer of JAX, is the Vmap or vectorized map that that have the ability to run a function. It's simple, like it's just like the pandas map function, but for this example, you can, when you call the Vmap, it tries to parallelize your code, or try to vectorize your code and run it across multiple GPUs and CPUs. Threads of your CPUs on a data frame or something like that. You can use it. You can actually stack those functions. You can transform the JIT transform on the Vmap to make it runnable on multiple CPUs. For example, you can use it for data augmentation, to augment your data during the pre-processing of your data, to augment it using the TPU or the GPU. There is three functions here: rotate 90, identity, and random rotate. And you can actually just call the Vmap on the random rotate or any function of those, and on the data set you have, and it will generate to random rotations and augment your data sets. There is also a Pmap similar to Vmap, but the Pmap can run across multiple devices and hosts and or TPU clusters or something like that. And the last feature that I'll be talking about is the GRAD, or the automatic differentiation. That gives us the ability to calculate the differential equations of our functions. To calculate the first order of the function activates, we call it once and with the value. And when you call it on a function, it generates for you a function. So you can call a value with that function. You can call that function with a value for the first example. And you can stack multiple calls of the same functions to receive the second order gradient. Excuse me. And there exists other features like scan for recurrent computation, JET, mask, remask, and FastSort, but then I'll not be going through them. One is the grad and JET. And so we'll be switching to a simple to the, let's just see the Kaggle notebook. Let me share it with you. Okay. Okay, it is. Yeah, this is it. It's here. Let's see. So this is just a simple introduction to JAX. It's not just simple introduction to JAX. As I said, we'll be switching to TPUs. Us to see. Okay, GPU is quite. There is a queue on TPU, so I cannot use this. I will be switching to GPU for just simple comparison. Okay. So we'll start first by looking at the matrix multiplication using a 3000 by 2000 2D array. It was generated with range. Using the matrix multiplication operator, it took us about 1 second, 1.40 seconds to run this this multiplication using the CPU. But when we use the GPU or the JIT, the JAX GNP, and use it to calculate this function, this multiplication, it only takes it 7 seconds. I don't know if you can see the screen or not. I think you can see the screen. And when you are trying to generate random numbers in JAX, there's a lot of text to a key that you can reuse this key to generate the random number you want. If you in NumPy, it updates your key, the original key. It's updated by automatically without having the ability to control the updation of that key. So you have the ability to pass this key and control the reproducibility of your solution or of your code. And same thing, it uses the GPU, it uses the CODA as you see here, and yeah. Now we will be looking through a simple implementation of linear regression with JAX. We will be using the make regression function from Escalon datasets that will help us to create a simple regression dataset. A dataset that is you can use it for a linear regression with with only one features, and we will be looking to results of this function here. So it's the x have 100 data points with one feature, and y is only one feature. Only 100 data points with one feature in them. Okay, so to visualize the data set we have with the x's, this is the y's and these are the x's, you can see that it's just a simple linear data set. We will be splitting them using the scikit-learn pre-processing, the trained test splits from model selection in scikit-learn to generate train sets and test sets, and to initialize the model. Our models will be initialize it with zeros that has a shape of 100. Just a simple linear regression like the one viewed in here. And of course, a forward or a predict function that will help us, given a set of parameters, and the dataset will help us calculate the dot function or the multiplication of those data points with the parameters W and plus the bodies. And in this example, we will be using the mean squared error to calculate the loss function of our model, and then use the grad the jax.grad to actually calculate the grad, to calculate the value of the grad, the value of the loss. And yeah, and then there is the gradient descent and the update parameters that I will try to update the parameters of our model using gradient descents with an alpha, with a given alpha that will be passing through parameters, and the grads that is generated afterwards here and calculated by the grad function, this grad function. And we will be training our model for about 50 blocks, and we will have an alpha or a learning rate of 0.05 to use it for updating the weights of our linear regressor. It uses the GPU, so it will be pretty fast. And yeah, those are results. I think I forgot to. Okay, I forgot to look through. Okay, so let's go back to the slides. Let me just go back. Okay. We'll be moving to the second part of this talk, which is introducing the Flax, a library that is based on JAX, and we will see how to use it with the optax and using it with TensorFlow datasets, and actually saving the model at last. A small preview of Flax. It is built on top of JAX, and it contains everything that you need as a machine learning or a deep learning researcher. It has model abstractions and also the all what you can do, what you need to do with machine learning as a machine learning researcher. You might want to write your code or your models or your models, yeah, as models or classes, and then use some of the functional programming to update the parameters or to train your model and stuff like that. It is quite rich with the features it provides, and you might want to. Most of researchers prefer PyTorch than TensorFlow, because just when you use TensorFlow, you have a big library or a big framework and ecosystem to use for you. But it is not mainly focused for the use of researcher. There are a lot of tools, great tools in TensorFlow, but they are not necessarily useful for machine learning research. So most of the researchers, you find that they are using PyTorch for research. So Flax and JAX in the past 2 years have been one of the new libraries or new frameworks that are the choice of machine learning researcher because of the easy or the similar feeling like PyTorch and the easy use of those of different features, and you can also use it to train models with the same code to train it on CPUs and GPUs and CPUs without changing anything. And so it becomes one of the preferred tools for many machine learning researchers, and it provides with purely functional abstractions, as same as JAX that use pure functions, and also it natively supports the shape inference or the PPK pack that can support the compact network definitions and different things. And the main philosophy of the Flax ecosystem is to minimize the indirection, like subclassing, functional calls, and stuff like that. It's actually has a bias against the inversion of control, and where you can prefer to duplicate code over abstraction of it. And it has many other features. And as I said, you can use the Flax with OpStax, and for example, for the OTT, that is also built on JAX for transports, optimal transport problems. You can also use the RLX for reinforcement learning, and also like Jira for graph neural networks, and checks for testing, and CLU for metrics and evaluation of your models. And the best one is the JAX to TEF that will help you transform, or that will help you translate your model or transform it into .h5 or TensorFlow, a model that can be run on TensorFlow ecosystem. To build a ResNet that the same as the one used in residual neural networks, block using the vanilla JAX or JAX, you use it like this. You declare you define a function called conv block that has a kernel size and filters and a set of strides. And then you call the conv from JAX dot stacks, I guess, to on your input, and to run it to build the same block using the Flax. You can use it like this. You subclass the NN models, and then define the results, or calculate the results of your residual nets block by defining or redefining the call function in the subclass of NN models, and then return it as a result. Everything here is not states, doesn't share any state with any other residual blocks, so you can actually also just add the JIT on it. We will be moving to a simple to the rest of the notebook before finishing the task. And just a minute again. Okay, let me share just. So to a simple Flax example, we'll be looking at this a simple Flax example. You can find the resources here that I used to building this notebook. We will be building a linear regression using only the dense nets, the five with 5 neurons. We define it just like NN, that is called from the Lenin package. And then again, we will define our random or pseudo-random number generator, and initialize it with the a 0 key, and then we'll return us the 2 keys that we will be using for one to generate dummy inputs just for this example, and the other one to feed it to initialize our model. And you can see that this is the model we have right now, the architecture of this model. And then you can apply the parameters to the inputs, and you will get the results of applying this model on the inputs we have. You can see that there is 5 neurons here, and this is the value of them. And we'll be generating new data to use it for a simple linear regressor with the Flax. We define here the mean squared error, and you can call on it. We use the decorator of JIT decorator, and then return the value of the JIT on the batch version, on the batch data of x and y, and because this is iteratable, so we will be using the Vmap to apply the squared error we defined here on the x batches and y batches. So this will be vectorized, and then this will make it run on multiple CPUs and GPUs. We will be using as a learning rate of 0.3, and the loss grad function we will be calling grad, the jax again dot grad, the value in grad on the MSC function. We defined the function to update the inner parameters of our model. And then we will be training the model for 101 epoch. No, sorry, I forgot to run this function here. And as you can see, the model is learning. And so another alternative way you can train your model, instead of building the update parameters for yourself and defining the gradient descent here, you can actually use Optax, an optimization library built by DeepMind, by DeepMind, to train machine learning models. It might seem familiar to TensorFlow a bit. You call the SGD, or stochastic gradient descent, with the learning rate, and then initialize the parameters of your model with the stochastic gradient descent, and then again call the grad, the value in grad on the mean squared error we defined earlier in the code log top, and then we will define a model with 5 features or with 5 neurons, and same as the code block at top. We'll just run this, and we'll train it again for about 101 epoch. And for this example, for each epoch, we will be adding the lost value to history, just for us to visualize it and look at how did our model perform. And to save the model, we will be using the serialization package from the Flax, where you have the ability to serialize it either to bytes or to state text and save it. As you can see, this is to save text. And if you want to load it, you can load it from bytes or from state text. And for this example, we'll be just loading it from bytes. And here is the model again that we saved earlier. You can see that they are the same values. Here it is. Same values. And also, as I said, fear not, TensorFlow is still useful for you, so you can use it. Actually, the best way to use it is with building data pipelines, because it is quite powerful at that aspect, and also using the TensorFlow datasets is quite helpful for that. So we will be importing the Flax and everything from we used earlier, and we will be building simple CNN models that will be using it on the nest dataset that has 10 classes. Here it is, 10 features, and we will be using a simple AlexNet model that is convolution followed with an activation function of ReLU, then an average pooling, convolution, ReLU, average pooling. It's similar to the way you code in PyTorch, and then flatten the whole CNN block, and then use the MLP, or multi-layer perceptron, to actually return us the outputs we want. Again, there is no softmax, there is nothing in here. You will have to build that, we will have to code it for ourselves. And let me just execute that. We will be using cross entropy. That is calculated using this function. And we will be labeling our labels using the one-hot encoder, and then the nuggets to actually calculate the softmax of this categorical cross entropy. And then to compute the matrix, the matrix, we will be using this function that calculates the loss and the accuracy of our model, and then bundle them into a dictionary. And the function to load the datasets a dataset from TensorFlow datasets and prepare them in train and test datasets, and split them into train and test datasets, and actually normalize them to transform them into a float 32 GNP arrays instead of tensors. And then again, just creating the train stack that will help us initialize the model. And the train step that help us train the model for one step. It takes as a parameter the state of the model and the batch you want it to train on it, and then just use the loss function and grade the loss function, and then use it to calculate gradients, and then apply them to the state of your model, and returns the states and the metrics it calculates using the compute matrices. And then an eval function that will help us evaluate our model. And to train the model for one epoch, we have to go across all the training examples we have. So there is a for loop that will be training to train the model on all the permutations of the data sets, and then update the model after each iteration or after each training step. Think on it, okay, and evaluate again the model. So to get the data set here, we will be just calling the different functions. For this data sets, we will just call in this function to download the data from the model. And this will take a lot of things. Okay, it's still downloading the data sets. And we will be again setting the seed of the randomness, and then setting the learning rate to 0.1 and the momentum for the SDG to 0.9. We will create the training set or initialize the model here, and then again. Okay, we'll be training the model 10 epochs with a batch size of 32. And for each epoch, we will be calling the train epoch function we've defined earlier. And to evaluate the model, we will be getting the test result and test accuracy from the eval function we've defined earlier. I think there is a problem with the CUDA version in this notebook. It's not actually updated. As you can see, here's the first epoch training. accuracy, and this is the test accuracy or the validation accuracy of our model. And it will keep on training and training and training until it finally. Okay, I think we've reached the end of our talk. Do you have any questions? Feel free to ask. Do you have any other questions? If you have any questions, feel free to ask. If you have any questions, feel free to ask. If not, feel free to contact me using any of the available contact information on the screen. You can find me on Twitter or Instagram or anything using the first one, the first personal tag, Taha Bouhsine, or you can use the, if you want to follow me on Kaggle or GitHub, you can use the Skywolf tag. It was a pleasure talking to everyone and sharing whatever information. I hope that you did get استفدتم من هذه السيشن. And if you have no question, welcome, Mustafa. If you have no questions, I'll see you in the next one, I think. Thank you very much, everyone.